Yeah. All right, good morning. So, today we have a busy schedule. In the morning, I am going to talk about nano-composites. So, the first lecture will be on thin films and core shell nanofibers, and the second one will be on core shell particles. So, in the afternoon, we have tutorial on the measurements of converse magnetoelectric effect by electric field tuning of ferromagnetic resonance. It's also added a very short lecture on one of the device applications, which we call gyrators. These are voltage to current converters or the other way around. These are pretty simple devices, and it's useful for many applications, including you are familiar with LED lights. So, you can put together a power supply with the use of composites for the LED lights. Okay. So, I thought you should be familiar with all different applications. There will be some more in the next 2 days. Okay. So, the first lecture I am going to talk about nano bilayers and core shell fibers of ferromagnetic and ferroelectric phases. Now, this one you saw in Dr. Mathe's lecture. This is about the mechanical connectivity between the two phases in a composite, a ferromagnet and a ferroelectric. So, we represent the connectivity with two numbers. There are two phases. So, the first number tells you the first phase, how it is connected to itself, and the second one the same way for the second phase, but just take a look at this 0 0. These are cubes of two different phases. They are represented by cubes of two colors. One is clear, the other is gray. So, if you look at the white ones, it's on its own, it's not connected to any other white ones in all three directions. So, it's a 0 connectivity to itself for phase 1. The same way for phase 2, it's not connected to itself any of the three directions. So, it's a 0 0 composite, and for 2 2, these are 2D layers of phase 1 and phase 2. They are connected to itself in the 2 dimension. So, you represent this by 2 and 2. So, all these magnetoelectric interactions, it's mediated by mechanical strain. So, it very much depends on how these two phases are mechanically connected to itself or the other one. Okay. There are a whole bunch of connectivities. I think there are maybe 10 or more. You can take a look at it. It's available if you go on Google image search and then type in mechanical connectivity for composites. It will come up with all these figures. Okay. So, there are a lot of resources on the internet. So, it's up to you to look for anything that's of interest. Okay. So, there is no shortage of information. There is so much available on the internet, and please take the time to look through them. And that's the only way to learn. This 5-day course, we can give you only so much, but everything else is, it depends on you. So, in the case of thin films, you can put together different structures. The first one is, nanoparticles of phase 1 embedded in a matrix of phase 2. So, it is a 0-3 composite film. The second one, it can be a nano bilayer or multi-layer on a substrate. So, it is a 2-2 film on a substrate. The third one is a nano pillar in a matrix of another phase, and these pillars and the matrix are on the substrate. So, that would be 1-3. Okay. So, there are many ways to make these thin films, and some of them are listed here. DC and RF sputtering. For example, in RF sputtering, if you want to make a film of some material, let us call it A, on a substrate, there will be a target of the material for which you want to make the thin film. So, you can use radio frequency energy to make a plasma of either argon or oxygen. If it is an oxide film, the high energy plasma would be made of oxygen. If it is metal film, you do not want to oxidize the film, it will be argon plasma hitting the target. So, it will break loose the materials from the target, and then you can deposit the film on a substrate. That is how the RF sputtering, or in the case of DC sputtering, you use a DC voltage to create the plasma. Now, in pulsed laser deposition, there is a high energy laser hitting the target, and that will break loose the materials for which you want to make the film. So, there is always a substrate on which the films are deposited. Chemical vapor deposition, you have a gas carrying the metal ions or anything that you want, and there is a substrate which is heated to maybe 400 to 600 degrees. So, when the gas flows on top of the substrate, the film will be deposited onto it. So, it is chemical vapor deposition or metallo-organic MOCVD, it is based on similar principle. Then you can use an electron beam to deposit the film, that is E-beam evaporation. Then molecular beam epitaxy. Liquid phase epitaxy is little bit more complicated, and there is, for example, you can make films of ferrites or garnets using LPE. So, if you want to make a film of some, say for example, nickel ferrite, you take lead oxide, heat it up to 900 degrees, and then put in nickel oxide and iron oxide to make a homogeneous solution. Then you dip a substrate into this. So, the film will grow, it is much faster film growth. So, LPE is the film you can make several microns, whereas all other techniques, they are very slow growth process. It takes forever if you want to make a film of several microns. So, all the other techniques except LPE, you come across films that are nanometer thick or maximum maybe 1 micron, whereas LPE you can grow films up to 100 micron within a few hours. So, it is a fast growing, fast growth technique, and at the same time you can make very good quality films. That is the one we use for our devices that operate at very high frequencies, because high frequency devices you need a thicker film compared to all other applications such as a sensor or of that kind. So, LPE is a very good technique, fast growth and quality films, and these are used for high frequency device applications. So, once you grow these composites, you have to find out how good they are in terms of the strength of magnetoelectric interactions. For the past 2 days, you have heard these so many times, direct and converse magnetoelectric effects. These are the effects of either the magnetic field or the electric field on the composite. And so, I will discuss the film of different systems and how these strength of the interactions are evaluated in those composites. Okay, so there are literally thousands of papers on thin films. So, I have selected a few examples that are of some interest probably to you. And the reason being, spin spray deposition is a very low cost technique that involves the use of nitrates or acetates, and you do not have to treat the film at very high temperature. These are very close to room temperature. So, you can take a look at these references to go through the details on how these films are made, but the bottom line is you can make quality films of spinel ferrites on any substrates with this low temperature process. So, there are several chemical reactions involved in this technique. So, I do not want to spend all my time discussing that and then missing the main point, which is how these composites are, what kind of interactions they have, and potential applications. Okay. So, the first example is nickel ferrite of this composition on lead zirconate substrate, and these are made by spin spray deposition process. The film thickness is about a micron. So, what is shown here is the magnetization of this film versus the static magnetic field. For example, you can use a vibrating sample magnetometer or a squid magnetometer to measure this kind of characteristics, magnetization versus H. Then what the people who did this work, what they did was to do this measurement under 0 electric field. Then they applied an electric field to the sample, which produced a piezoelectric strain, and that altered the magnetization versus H behavior. So, that is what is shown in two colors. One is without electric field and the other is with electric field. There is a small change in the magnetization, that is, you can find the increase or decrease in the magnetization because of the electric field. Take the ratio of the change to the applied electric field, that is a measure of the strength of the magnetoelectric interaction. So, the other system number 2 I want to discuss is once again zinc, iron and oxygen. This is kind of zinc ferrite. It is not completely zinc alone. There is only 10% zinc and 90% iron 2 plus. That is the way the composition works. So, this one has zinc 2 plus 0.1, iron 2 plus 0.9, then Fe 3 plus 2 and then oxygen 4. So, everything has to add up so that it's it's stoichiometric as well as charge neutral. That's important. Okay. So, the oxygen is 2 minus, 4 of them would be 8 minus. So, if you add up all the metal ions and find the valency, it will be exactly the same as the one for oxygen with the negative sign. So, it is zinc ferrite on PM and PT, single crystal substrate, and the deposition was once again by spin spray at temperatures less than 90 degrees Celsius, and the authors used converse magnetoelectric effect to find the strength of the magnetoelectric interaction. So, what they did was to look at the ferromagnetic resonance under 0 electric field and a series of electric fields from 0 to 6 kilovolt per centimeter. And as you see here, this one starts with 0 electric field, then 2, 4 and 6. As the electric field is increased, there is a shift in the resonance field. So, the resonance field is wherever this horizontal line and this profile when they intersect. So, there is a shift up from 0 to 2 kilovolts, 4 and 6, and they came up with the number of 23 Oersted shift per 1 kilovolt per centimeter. So, if I apply an electric field of 1 kilovolt per centimeter, it will shift the ferromagnetic resonance field by 23 Oersted. That is a good enough number for you to conclude that there is indeed a strong converse magnetoelectric effect in this particular system. And this is magnetite Fe3O4 spin spray film on PM and PT, and the next one will be on PZN-PT, lead, zinc niobate, lead titanate. Once again, the converse magnetoelectric effect was studied with electric field tuning of ferromagnetic resonance, and the profiles are shown here, and there is a shift in the resonance field with the application of the electric field, and it goes, it is a downshift in the ferromagnetic resonance profile. The overall change in the resonance field is about 600 Oersted, and so they came up with this number. So, the converse magnetoelectric coupling coefficient is 67 Oersted centimeter per kilovolt. That is better than the previous case where it was only 23 Oersted centimeter per kilovolt. And the film on PZN-PT had even higher magnetoelectric coefficient. It is 108. The reason being that PZN-PT has a much higher piezoelectric coefficient than PMN-PT. And that is the reason for the stronger converse magnetoelectric effect in this particular system. So, there are also other types of films. For example, the one shown here is an alloy film of iron, gallium and boron on single crystal PZN-PT substrate. And once again, the ferromagnetic resonance was used for characterizing the converse magnetoelectric effect, and also they did the measurements of the magnetic hysteresis M versus H under an electric field. So, under FMR you look for the change in the ferromagnetic resonance field, and when you do M versus H under electric field, you look for the change in the remnant magnetization, that is the magnetization at 0 magnetic field. So, that is the intercept on the vertical axis corresponding to H equal to 0, and you see a distinct change in the remnant magnetization under an electric field. So, you can look for the fractional change and come up with a number for the converse magnetoelectric effect. and then terphenol D, PZN, PT. So, in this work, the authors, they sputtered 100 nanometer thick terphenol D film. So, terphenol D is an alloy of terbium and dysprosium and iron. So, they made an alloy with this particular composition, terbium 0.3 and dysprosium 0.7. So, terphenol D is very sensitive to the content of terbium and dysprosium. So, everything changes, the magnetization, magnetostriction and so on. So, they did the deposition at a series of temperatures at which the substrate was. The substrate was heated to 550, 650 and 750 degree Kelvin, and they did the deposition. And as you see here, the measurements on the converse magnetoelectric effect was done by M versus H under an electric field or ferromagnetic resonance under an applied voltage, and they came up with very indication for very strong magnetoelectric effects in this particular system. All right, this one is a 03 type particulate nanofilm on a substrate of PZT. So, the cobalt ferrite is the magnetic phase in this particular system. What is shown here is the scanning electron microscope picture of the surface of the film. You see these black spots, these are cobalt ferrite as you look down on the nanopillars. So, it is in fact a nanopillar in the PZT matrix on a substrate, and the one on the left, it shows the X-ray diffraction data. So, each phase here, that is cobalt ferrite and PZT, then the incident X-ray is reflected. So, there is a detector that scans the angle of reflection, and then it will record the intensity of the X radiation as a function of this angle. So, depending on the lattice structure, the X-rays are diffracted into forming a series of peaks. So, you can identify the phase of the material from the position of these angles. It is a traditional technique to find out if you have the material what you really want, and also if there are impurities, you will see additional lines that can be identified. Now, there are data available from past researchers. So, you can compare what you get, what should be the case, and then identify all these different phases. So, in this particular system, it is cobalt ferrite nanopillars in PZT, and then they measured the magnetoelectric voltage coefficient as a function of bias field at series of frequencies, and these numbers are it's okay, it's not great, but they are very decent, because you have to keep in mind that these are nano pillars of cobalt ferrite. That would mean that the amount of cobalt ferrite present in this system is very small compared to the amount of PZT. You get the maximum magnetoelectric interaction only when both phases are present in equal number. It should be 50-50, right? But that's here it is not 50-50. You can easily look at it. These are tiny nanopillars in a huge matrix. So, obviously, it is going to be not so strong, the magnetoelectric interaction, and that is reflected in this number for the voltage coefficient. This is vertical heterostructure. It is also cobalt ferrite nanopillars in barium titanate matrix, it's similar work. So, what I want to point out here is, look at this figure. What it shows is that, barium titanate goes through a phase transition, crystallographic phase transition at around 360° Kelvin. Above this, it's cubic. Below this, it's tetrahedral or some kind of distortion. So, what happens is, above 360, barium titanate is perfectly cubic. So, the center of positive and negative charges, they coincide and there is no separation between the two. So, the polarization is 0 above 360. When it is cool below 360, there is a small shift in the position of barium. So, that would result in a separation between the center of positive and negative charges, which would mean that there is an induced polarization that comes because of the shift in barium atom position. And in this particular system, the ordering of this dipole ordering, when barium titanate goes from paraelectric to ferroelectric, it also changes the magnetization for the cobalt ferrite nanopillars. So, that is an evidence for magnetoelectric interaction in this particular system. Right, this is bismuth iron oxide and cobalt ferrite 1,3 type nanostructure. It is the cobalt ferrite nanopillars in a matrix of bismuth iron oxide, and the one here shows the atomic force microscopy picture of the topography. It is a surface of this system, and here you see the magnetic force microscopy image of the same one. So, the black and white spots are the domains of the cobalt ferrite, and look at this color, there is it's white spot, and then what this one is, it is they apply a field of 20 kilowatt up perpendicular to the film, then it is 20 kilowatt also perpendicular, but in the opposite direction. So, there is a change in the domain orientation, and that you can see very clearly in these two pictures, the change. And here what they did was, under this condition with 20 kilowatt field, they also applied a voltage or an electric field that led to a switch in the domain orientation. So, this rectangular part, you can see the bright spots turning into dark one. So, it is domain switching of the cobalt ferrite due to magnetoelectric interactions with bismuth iron oxide. The same case here, the magnetic field is in the opposite direction compared to this. Then once again you apply a voltage that is minus 16 volts, there is a switch in the magnetic domain orientation, and this is what you observe. So, these are evidence for coupling between the two phases through mechanical strain. Okay, so I just talked about different types of nanofilms, and then how people did prepare them, and also some studies on the strength of the magnetoelectric interactions, either by looking at magnetization versus H under electric field, or ferromagnetic resonance under an applied voltage. Okay, now let us move over to the other topic, and this is core shell nanofibers of a ferromagnet and a ferroelectric. So, in this talk I am going to focus on all oxide system. The ferromagnet, the phase in this work would be a spinel ferrite on a hexagonal ferrite, and the ferroelectric would be either barium titanate or PZT. So, I will talk about synthesis of these coarse fibers by electrospinning, then characterizing the films by a series of microscopy techniques, including scanning electron microscopy, magnetic force, and scanning microwave microscopy. Then traditional ferromagnetic characterization by magnetization and doing FMR, and similar ferroelectric characterization. And then we were able to assemble these coarse fibers into a 2D or 3D film with the aid of a magnetic field. Then we did the characterization of the magnetoelectric interactions. It is rather difficult to make measurements on a single nanofiber because they are tiny. So, instead what we did, we assembled them into films on a surface or between two electrodes, and we were able to make these measurements. So, we used for the ferromagnetic phase either nickel or nickel zinc. These are spinel ferrites, and also a series of hexagonal ferrites M, Y, and W type. For the ferroelectrics, either PZT or barium titanate. So, this you have seen already. So, I will skip this. Hexagonal ferrite, they have obviously hexagonal crystal structure. The building blocks are spinels and tetragonal. So, there are different types based on how these blocks are arranged. They are called M type, Y, W, U, and so on. But do not bother about understanding how each and every one is stacked. It is not really important. But what you need to understand is there are certain types, and they are associated with the presence of a very strong magnetocrystalline anisotropy. So, in these structures, there is significant spin orbit coupling. It is coupling between the spin of the electrons and the orbital motion that leads to locking the magnetic moment in a particular direction. So, that is what we mean by magnetocrystalline anisotropy. It is as if there is a magnetic field present in the system, and that is rather high for the M type ferrites. It can be as high as 17 kilo-Oersted in a particular direction, which we call the C axis. So, M type has uniaxial anisotropy field along the C axis, and at the same time they have very small magnetostriction. So, some of the composites with M type hexagonal ferrites, the magnetoelectric effect is not very strong, but the advantage is that they have a built-in magnetic field. So, under for different applications, you may be able to use the composite as it is without having to apply an external magnetic field, because it is self-biased. There is a field present in it, and that is the advantage with some of these composites. And this is Y type, it has also an anisotropy field, but the anisotropy field orientation is not uniaxial, it is EC plane. The anisotropy, it is in the C plane of the ferrite, but the magnitude is somewhat smaller than for the value for M type ferrites. For Y type, it can be anywhere from 9 to 14 kilo-Oersted, but these are EC plane, and it has little bit higher magnetostriction, some of them as high as 15. W type also, it can be either easy plane or uniaxial anisotropy, and the magnetostriction is certainly much higher than what we get for M type. Okay, so how do you make these nanofibers? So keep in mind that we have to have these fibers in such a way that core is made of one phase, the shell is made of another phase, so that they have a clean interface. And the way the interaction takes place is that when I apply an electric field or a magnetic field, the strain in either the core or the shell is transferred to the other phase, and there will be a response from either as a change in the magnetic moment or a change in the electrical response. So how is it done? This is called electrospinning. The first step in the process is you have to make a solution or soul of the two phases separately, the ferrite and the ferroelectric. It's a long process. It takes 1 or 2 days. So the ferrite soul or the ferroelectric soul is made by taking nitrates. So if I want to make a soul of nickel ferrite, so you have to take nickel nitrate and iron nitrate, dissolve it in alcohol, add a polymer which is PVP, and then keep stirring it, and it may have to be done at a slightly higher temperature, less than 100 degrees, and there is a magnetic stirrer constantly stirring the whole solution until you get a clean solution of the whole product. So you take the soul and then load it onto 2 separate syringes. Then the 2 syringes are loaded onto a syringe pump. So the syringe pump has either 1 syringe or 2 syringes, and you can set how fast you want to dispense the 2 souls to the 2 syringes, and the end of each syringe is connected to a stainless steel needle. The needle itself it has dual chamber. Since you want to make a fiber with a core and a shell, so we use a dual chamber syringe that's shown here. So the soul from the one of the syringes will be fed through the core, and the soul from the other will be fed through the side one here. So this soul will form the core, and the soul through this one will form the shell. So this is how the interior looks like. At the tip, they come out as it is. Now there is an electric field applied between the this needle, and there is a drum made of aluminum. This collects all the fibers. So this is at a positive potential relative to this. This is ground. So you apply 15 to 20 kilovolts for a distance of 10 centimeters. So the electric field is 1.5 to 2 kilovolt per centimeter. So when the soul comes out of the end of the needle, these particles get electrically charged. So as you know, they are charged with a positive polarity. So as the charge comes out, these particles, positive and positive, they will repel each other, they will diverge. So it forms what is called a Taylor cone. So this is, so as the particle comes out, there is polymer, it's drawn into a fiber. So the fiber will have a core and a shell of these materials. But keep in mind that the core and the shell are in the form of nitrates or acetates. They are not fully formed nickel ferrite or PZT. So you have to collect the fiber and dry it at room temperature. Then you have to heat it up to much higher temperature, so that there is a lot of polymer in it that has to go, and also you have to form the two phases, both the ferrite and the ferroelectric. So, the processing temperature is anywhere from 600 to 1000 degrees. So, once you make it, then you have a fiber with a core of material A and a shell of phase, different phase. Okay. And so, how do you control the dimension of the fiber? There are many ways to do it. One is you can choose needles of different diameter with core diameter and the shell thickness that you want. That is one way. Then you can always play around with the electric field that you apply during electrospinning. Solid viscosity also can change the fiber dimensions, and the entire electrospinning setup is in a closed chamber of plexiglass, and you have to control the humidity. If the humidity is very low or very high, it can mess up the fiber, you do not get what you want. So, these are the parameters that would control the dimensions of all these fibers. And so, we did some of the measurements. You take 100 fiber and look at the diameter, and as you see here, there is a wide distribution in the diameter of the fiber, and it is anywhere from 100 nanometer all the way up to 300 nanometers. But keep in mind that 2/3 of the fibers, like 66%, it has a very narrow range. So, even though there is a wide distribution, diameter at lower end or at higher end is not that many. So, there is always you can define the fibers with an average diameter, 66% would be in the range of 140 to 180 nanometers. Okay, these are some of the SEM images, and what you see here top left is a bunch of fibers. You see different dimensions, and the one in the center is an isolated fiber with PCT core on the nickel ferrite shell, and you see very clean interface, and it is the core seems to be of uniform diameter, and the shell thickness is also quite uniform. And this one has PCT core, and this one has nickel ferrite core PCT shell. Okay. And we did X-ray diffraction, and there are no impurities in this particular system. And this one is magnetic force microscopy image of the same set of fibers with either PCT core or ferrite core, and the domains in the nickel ferrite, they look, one is bright, the other side is dark, because as it comes out, the domain on this side has an orientation opposite to the other one. But PCT being non-magnetic, it looks dark in the both cases here. And scanning microwave microscope, it is an imaging technique using a tip made of microwave frequency radiation. What it does is, it images the fiber in terms of high frequency impedance or capacitance. So, it will differentiate the core and the shell with distinct contrast in the color. That is what you see here. These are images at series of frequencies, and you see a very clear image at this particular frequency. That is because there is impedance match between the microwave cone and the fiber itself. That gives you a very clear image, and this one has pretty good resolution, and it shows uniform core, and the shell thickness is also pretty uniform. Okay, so these are similar fibers with M-type ferrite and barium titanate for the ferroelectric phase. Once again, this is X-ray diffraction, and these are scanning microwave microscope pictures for the core and the shell. And you see all these messages in these, all these images, the core and the shell very well resolved. These are similar images for Y-type ferrites and either PZT or barium titanate. And we did the traditional magnetic and ferroelectric characterization. This one shows the magnetization versus H for some of these core shell fiber systems. And these are the polarization versus electric field. And these numbers are pretty small. It's nanocoulomb per centimeter squared. For traditional thin film or bulk PZT or barium titanate, this is 1000 times larger. It's microcoulomb, this is nanocoulomb. That's because as you go smaller in dimension, all the properties change and for the worse. So in this particular case, we found that the polarization for nanofibers are quite small compared to either bulk or thin films of PZT or barium titanate. Okay, so to measure the magnetoelectric interactions, we ended up assembling these fibers into thin films in a uniform or field gradient. In both cases, the field applied was magnetic field. So you can apply an uniform field with an electromagnet or a solenoid. And for non-uniform or a field gradient, all you have to do is use a permanent magnet. So in the case of non-uniform field, the fibers will be pulled towards the region where the field gradient is maximum, whereas in the case of uniform field, so you will see the fibers aligned along the field direction. That's what you see in these two pictures. Here there are regions where higher concentration of fibers are there. This one shows pretty uniform and the fibers aligned along the field direction. This one we did like a matrix. We just applied a field along this direction, for example. So the fibers align along the field. Then we added another layer of fibers and applied a field in the perpendicular direction. So it's like a matrix. That's what you see here. So for characterization, we used low frequency magnetoelectric voltage coefficient, and also we did polarization versus electric field in the presence of a magnetic field. These are the two techniques. All right, here what I am showing here is for a disk of these fibers, we did polarization versus electric field with and without a magnetic field. So the insert here shows P versus E electric field for H equal to 0 and 7 kHz. As you see here, when we applied a magnetic field, there is a decrease in the remnant polarization. So what's plotted here is the ratio of the change in the remnant polarization to the original value when there is no field in percentage versus H. So you start with 0 field, there is a decrease in the remnant polarization. So that is indicated by this negative number. So the magnitude keeps increasing to about 2%. So when you start decreasing the field, it doesn't quite go follow this trend. It still keeps decreasing, and there is always a memory effect. So overall this magnitude of fractional change in the remnant polarization of 2%, that is the maximum value. It is pretty, you may think it is very small. This is H-induced polarization in a composite, and this value is much higher than what they measure in single phase multiferroic systems. In single phase systems, you may get 1% change for a field of 5 to 6 Tesla, that is 50 to 60 kilo oersted of static field, whereas here we are talking about less than 1 Tesla of H, and that is a significant change. And these are similar data. The previous one was for fibers with PZT core and nickel ferrite shell, and this one is nickel ferrite core and PZT shell. And look at these values here. The fractional change in the polarization, in the previous case it was negative, in this one it is positive. So, the strain in one case is compressive, in the other case is tensile. That is the reason for the change in the sign of the polarization, decrease or increase. And once again, there is always a hysteresis, it keeps going up, and then when you start decreasing the field, the trend continues, you end up with a maximum change close to 30% for these fibers. And we did similar measurements for nickel zinc ferrite. So, what happens here is, depending on the zinc concentration, the fractional change can be as high as 50%. That is what I want to emphasize here. But apart from that, all we can infer from this data is that there is a very strong magnetoelectric interaction in these core shell fiber systems, and it is indicated by these measurements. Okay, so this the previous case it was nickel ferrite or nickel zinc ferrite and PZT and barium titanate. These are similar data for systems with hexagonal ferrite and PZT. So, this is M type. Once again, the strength of the magnetoelectric interaction was evaluated through measurements of P versus E under H, and these magnitudes here are rather similar to what we saw for spinel ferrites, that is nickel ferrite or nickel zinc. So, the maximum value in this system is around 20%, either with PZT or barium titanate. And so, we also measured the low frequency magnetoelectric voltage coefficient in 2D or 3D films of these fibers. So, they were made by you dissolve the fibers in ethyl alcohol and spread it on a glass slide between two electrodes, and then you apply a magnetic field. So, these fibers will align along the field orientation, and depending on how much fiber you use, the film can have highly concentrated fibers or thinly populated fibers. Okay. So, if you have a film with very low concentration of fibers, the overall magnetoelectric voltage coefficient will be small. But if the concentration is high enough, you will have a much better value for the voltage coefficient. And here the values are rather low, it is 3 to 4 millivolts per centimeter Oersted, and these are 2D films. And when I go to 3-dimensional films, these were assembled between two copper plates, and once again the fibers are placed between the two plates, and you apply a magnetic field to orient them along the field direction. And in this case, the numbers you see here are much better than the previous one. Okay. It's here 3, and whereas here it is 5 times higher. Now, the one thing I want you to notice is when the bias field is 0, there is a finite voltage coefficient. It is not 0 as in this case. The one in the top, the bottom left is a bilayer of a platelet of nickel ferrite and PCT. Here at 0 bias field, the voltage coefficient is 0, whereas here with strontium ferrite, barium ferrite core or strontium ferrite PCT core fibers, the value at 0 field is always quite high. That is because of the self-biasing effect, because M-type ferrite has very high magnetocrystalline anisotropy. So, you do not need a biased magnetic field to get a decent strength for the magnetoelectric interaction, even in the absence of an external biased magnetic field. These are similar data for different hexagonal ferrite systems. Okay, so what do we do with all these fibers? You can put together magnetic sensors for different applications. For example, sensors for biomedical imaging, and the one on the left shows magnetocardiography, and at this time it is done with a squid magnetometer, and you can use high temperature superconductors to operate them at liquid nitrogen temperature. The magnetic field produced in cardiac activity is around 20 picotesla, and you can easily put together sensors of these coral fibers or thin film, which would be able to measure this kind of magnetic field. So, you can replace the squid magnetometer with an array of these sensors. If they are self-biased, it is for the better. Okay. So, right now the technique with any squid magnetometer is very expensive. So, not many people can afford to have the magnetocardiography done if they are sick. Whereas, if you can make it with these sensors made of the coral fibers or any thin films, then it is rather going to be inexpensive. But so it will be along the circumference of the collector.
So you cut and we get the sheet and you directly.
Yeah, right. So we collect it and then you dry it at room temperature for a day. Then you put it in a crucible and then fire it up. But you have to be very careful when you heat it up and cool it down. If the heating and cooling rate is very fast, they will crumble into particles. You won't have a fiber. So to keep the fiber shape, we heat or cool at the rate of 0.25 degrees per minute. So it's very slow heating and slow cooling. Can you do what?
Like electrodes.
Yeah, these are electrodes. We sputter them. So it's made of titanium and platinum in our RF sputtering system. Then you can place the fiber in the alcohol solution between the two electrodes, let it dry. Then you form a film in either 2D or 3D, and that's used for measuring the voltage coefficient. For measuring the polarization versus electric field, we use the disk of the fibers. You collect all the fibers, press into a disk, and the disk has to be annealed at high temperature so that it has some mechanical strength. then you have to have electrodes spotted on it, then only you can measure the polarization versus electric field.
So have you fabricated any sensors?
I'm sorry, what?
Sensors? Have you fabricated any sensors? Final product that can sense the visual tone, can sense the field of the heart. Any sensor level have you?
Can you repeat the question?
Have you fabricated any sensors sort of?
No. See, the numbers I showed you, the voltage coefficient, they are pretty small, right? It's just a few millivolts per centimeter arrested. So we have to find a way to improve the voltage at least a few hundred. Yeah, right. So we are not close to making a sensor out of it. So it's a long way to go.
So you have said that humidity also plays an important role in the fiber process, right? So what is the expected value of humidity? It depends on the different ferrite system, or like it's general?
Yeah, the idea is to improve the quality of the fibers, and so also you can, instead of nano, you can go to micron sized. So scaling up the process to make micron size core and shell, and also you want to keep the geometry without any defect, right? So the key is to have a clean interface. It may be easy for nanometer thick films, nanometer dimension of core and shell, but when you go to micron size, there may be some defect which would affect the overall transfer of mechanical strain from one to the other. So there are technical challenges, but one has to find a way to improve it. It can be done, it should be done, but somebody will do it, maybe not us. All right, so shall I go to the next one? Or?
If you want a 5-minute break, that is also okay.
Yeah, I can take 5.
Fine.
Okay, yeah.
Just repeat the summary page for a live recording. It's power off, so it's
You want
just-
to say something? Okay.
yeah.
All right.
Repeat just summary page.
Yeah. All right, just a quick summary of what we discussed so far. So I talked about the magnetoelectric coupling in nano bilayers as well as core shell fibers, and so in the case of thin films, we looked at different types of films, either nanoparticles in a host matrix, or a nanopillar, or a nanobilayer. So for core shell fibers, the focus was on fibers of spinel ferrite and a ferroelectric, or hexagonal ferrite and a ferroelectric. And the traditional methods for exploring the nature of the magnetoelectric interactions in all of these systems are either ferromagnetic resonance under an electric field, or magnetization versus H under electric field. These two for converse magnetoelectric effect. For direct magnetoelectric effect, people used measuring P versus E under H, or the low frequency magnetoelectric voltage coefficients. So in a nutshell, the nano systems have a much weaker magnetoelectric interaction strength compared to bulk or thick film composites. So there should be some effort, serious effort on our part to enhance the strength of the interactions in the nano systems if you want to use them for any applications such as biomedical imaging or miniature sensors. So there is a long way to go. So this is just a starting point. Okay, right. Thank you. Is this okay? Or? All right. So the second part of this morning session is nanostructures 2. So here we are going to deal with coarser particles of our magnetoelectric composites. So in this talk, I am going to focus on coarser particles of nickel ferrite and barium titanate. Okay, and I am going to talk about assembling the coarser structure by two different means. One is using chemical self-assembly, the other is using DNA assisted assembly. So we did this work with collaboration with our chemistry colleagues, both chemical assembly and the DNA one. Okay. So let's see. So the coarser nanoparticles, they were assembled chemically by attaching two complementary coupling groups. So you attach one group to the ferrite, the other group to the ferroelectric, then bring them together in the presence of a catalyst, and they form coarser structure. In the second one, with the DNA assisted assembly, as you know, the DNA has a helical structure. We were able to get functionalized DNA linkers. The linker, if you unwind the DNA, you get two strands, right? So Yale has a lab where they functionalize the complementary strands, and we are able to get that. Then the two strands were attached to the ferrite or the ferroelectric, then you bring them together, then the DNA will hybridize, then that's how that assembly works. So fibers, we already talked about it, and so the chemical self-assembly, we used particles of barium titanate and nickel ferrite, and they were assembled and characterized by a variety of imaging techniques, including transmission electron microscope, scanning electron microscope, and also various scanning probe microscopy, including AFM, MFM, and SMM. And they were also characterized with magnetic and ferroelectric measurement techniques, and we assembled these coarser particles into superstructures in a uniform or non-uniform magnetic field. And of course, you have to study the nature of the magnetoelectric coupling. For that, we use P versus E under H, magnetodielectric effect, that is change in the dielectric constant when you apply a static magnetic field, or also the ME voltage coefficient. We did some theory, and then the theory predicted strong magnetoelectric interactions for coarser particles. For example, we did some simulation for a core of 50 nanometer barium titanate and a shell of 10 nanometer nickel ferrite, and we came up with very strong interaction strength through the calculation of ME voltage coefficient. Once again, these numbers were obtained for the parameters that are good for bulk materials, not for nanomaterials. So these numbers are highly misleading because we didn't know these magnetostriction and piezoelectric coefficients for nanoparticles. So that's the shortcoming in this model. But in any case, the theory predicted strong interactions, and that was the driving force behind doing these experiments. Okay, so what is the procedure for chemical self-assembly of the coarser particles? The first step is to synthesize barium titanate and nickel ferrite nanoparticles. We did that for nickel ferrite by co-precipitation, and for barium titanate we did not make them. We just purchased from vendors. There are many companies that would sell nanoparticles of barium titanate, the size that you want. Now you can mention the size 10 nanometer or 100 nanometer, but there is always a range of particle size in whatever you get. So all they guarantee is a majority of the particles will be that particular size, and there will be particles on the high and low end of the spectrum, but most of them will be what you want really. And then the second step is to functionalize these particles with two complementary groups. The groups that we used, one is called alkyne group, the other is acid group. Then you bring them together in the presence of a copper catalyst, and there is what's called a click reaction that happens, and that's how the core structure is formed. And somebody who invented this click reaction, they were awarded the Nobel Prize some time ago. Okay. So it's a neat technique. The key is, if you assemble a core shell particle, you have to make sure that it's stable at room temperature, because everything in the universe, it has a finite energy, that's called thermal energy. Anything at room temperature will have K times the temperature. K is the Boltzmann constant. So the bonding strength should be large enough to overcome any thermal agitation or dissociation due to thermal energy. So you need to make sure that the core shell particles can overcome the thermal energy and they stay intact as core shell particles, not dissociate into fragments. So I don't want to go into the detail how these attachments are done. It was done by my students and postdocs. I didn't ask them how they did it, but it was a long procedure. It takes a couple of days, and the procedure is described here. I don't think it's really important, but all that you do is it involves a variety of solvents and exposure to UV radiation and so on, and then rinsing with methanol and all those things. But at the end of the day, you have two particles functionalized with alkyne group and acid group. The question is, how do you know the attachment was successful? How you know that you have decorated your nanoparticles with two complementary groups? That is done through infrared spectroscopy. And what is shown on the left and the right is that the IR spectra before and after attachment. And these peaks that you see here, that is evidence for that the attachment did happen. Okay? So these groups have specific signature in the IR spectrum, and you have to make sure that they do show up, and they did show up. So we concluded that the attachment was successful. Then you bring them together in the presence of a catalyst. So by the way, the two groups, one group attaches itself to the barium in barium titanate, the other one to the iron in the nickel ferrite, and the attachment is quite strong. It can overcome the thermal energy at room temperature, and then when you bring them together in the presence of the copper catalyst, the click reaction takes place, and the bond is very strong, and it can withstand any kind of thermal energy, at least until room temperature and slightly above room temperature. And you see some of the STM images showing the core shell particles, and the top one is, it is 100 nanometer core of nickel ferrite and 50 nanometer shell of barium titanate, and you can do simple calculation which we did, and in this case in 2 dimension you must have 8 barium titanate around the core of 100 nanometer nickel ferrite, and that is what you see at least close to it. And the second one, the middle one is, we also used 50 nanometer barium titanate and 10 nanometer nickel ferrite, and you see the STM image of that. And the third one is 100 nanometer barium titanate, 10 nanometer nickel ferrite, and a cluster of that. But you have to be careful, you can't keep decreasing the particle size, because below a certain size, nickel ferrite would become super paramagnetic, it no longer ferromagnetic, and you lose the very property that you need for magnetoelectric interactions. If it is too small, there is hardly any magnetostriction in nickel ferrite, then you may get core shell particles, but there is no magnetoelectric interaction. Okay. So, the optimum size would be at least 20 nanometer for nickel ferrite or above, and the threshold for barium titanate is probably 50 nanometer to maintain the ferroelectric nature. And these are some of the X-ray diffraction. We made sure that we did not end up with any impurities, and this one is SEM picture showing a core of nickel ferrite and a shell of barium titanate. You clearly see distribution in the size of barium titanate. It is not uniform, it is not just 50 nanometer, there are small ones and a bigger barium titanate. And we also did chemical analysis, and we made sure that we do have nickel ferrite and barium titanate in it. And these are scanning microscopy images for the core shell particles, and it's the capacitance image at a series of frequencies 2.3, 7.3, 14 and 19. As you see here, you see a very clear image of the core and the shell at this frequency, because this is where the impedance match between the particle and the tip of the SMM, that's very good match between the two. And also you see a very nice core, and the shell is of course made of nickel ferrite of different size. It is not exactly 200 nanometer, there is a distribution in the size, but you do have a core and a shell for sure. And this is SMM image for a collection of particles at 16 gigahertz, and all of them show a well defined core and a shell. This is magnetic force microscopy phase image for core shell particles. The center is the core, which is the dark region, and the shell is the brighter one. So, we are sure that we did form a core shell structure under these conditions by chemical self assembly. The next one is DNA assisted assembly. So, people are asking, why did you use DNA? So, the answer is, look at yourself. DNA is the building block for anything that is living creature. It can be a tree or an animal or humans, and everything grows according to what it should be. We don't grow fingers all over the body, it's where it is. So, it has the driving force to organize itself in a proper way. So, we thought that if you can use DNA to assemble these core shell particles, maybe it's easy to form superstructures. So, we didn't form any superstructure other than using a magnetic field to assemble them into films. But people in the future, they may take this initial study and build on it to make superstructures of these composites, hopefully. So the attachment works like this. As I told you, we got the complementary strands of the DNA from Yale. They are functionalized with alkyne already. So all we needed to do was attach A side group to nickel ferrite and barium titanate, then bring the DNA and these, and then attach the alkyne functionalized DNA to A side functionalized barium titanate or nickel ferrite in the presence of a copper catalyst. Then you bring the two particles with complementary strands of DNA close together, they will hybridize and form core shell structure. If you heat it up to 80 degrees, they will dehybridize and separate. So by heating and cooling below and above 80 degrees, you can either make core shell particles or make them separate. That was the whole idea, and we did just that. Yeah, so these are the two complementary strands of DNA attached to barium titanate and nickel ferrite. Then they are brought together, and then you cool it down to 25 degrees, they will hybridize, or you heat it up to 80 degrees, they will become separate. And these are some of the images for the core shell particles assembled with DNA, and you see a single particle with a core and a shell all the way to the left. The center one shows a similar core shell particle, and this one is a string of core shell particles, and this one is a collection of these particles. And we used magnetic force microscopy and scanning microwave microscopy, and the core shell particles are shown in the MFM topography and phase image here. And this is scanning microwave microscopy, and it can see through the core shell structure, and you see a very well defined core, in this case nickel ferrite, because the nickel ferrite has a much lower dielectric constant compared to barium titanate. So this is a capacitance image. So the capacitance for the shell will be the shell is made of nickel ferrite, so the capacitance is much smaller compared to the core. So the core looks here as a bright spot, and the shell as a dark one. This is AFM topography, and this is the capacitance image at 14 gigahertz. Okay. So these are core shell particles. Then we applied a magnetic field, then bring these core shell particles together to form a superstructure. And that's what you see here. So we just put these core shell particles in alcohol in different concentration, and then apply a magnetic field. They orient itself along the field direction. And this one is the case under very low concentration of core shell particles, but you see a very nice alignment along this line where the field direction is. This is at a little bit higher concentration. The streaks of these lines, they indicate the field direction, and the core shell particles do align itself along this direction. So that would mean that the nickel ferrite that we used was indeed ferromagnetic. Otherwise, it won't line up the way it is seen in these images. These are at much higher concentration of particles, and this is in a non-uniform magnetic field. So, as you see here, there are regions where the particles are concentrated. These are regions of high field gradient. So, the force is maximum along this region, and they line up in this. And these are at different concentration, and initially they were heated up to 80 degrees, then they dehybridize, then apply a magnetic field, cool them down, and they hybridize and then line up along the field direction. And especially this one looks nice. And also we assembled this in a rotating magnetic field. The magnetic stirrer, it was just rotating. You spread these particles and you see nice rings of these coarser particles under a rotating magnetic field. All right, so now we characterized these coarser particles in terms of magnetic properties and ferroelectric properties, and you see traditional M versus H expected for a ferromagnet. So, the nickel ferrite is indeed ferromagnetic. That's what we used in these coarser particles. And once again, the polarization is in the scale of nanocoulomb. It's much smaller than the barium titanate film or bulk material. So, the piezoelectric effect is rather very weak in these nanoparticles of barium titanate. So, we measured the strength of the magnetoelectric interaction by two different means. One is low frequency magnetoelectric effect. You are familiar with this. These measurements were done on 2D films assembled between two copper electrodes that are shown here, or assembled between two copper plates. This is a 3D film. So, see, for the 2D film, the interaction strength is very weak. It's reflected in the value of the voltage coefficient, which is in microvolt per centimeter Ørsted. In the 3D film, it is millivolts per centimeter Ørsted. It's still small compared to bulk materials, but it is it's a factor of 100 or 1000 better than 2D film. And this one is also a 2D film, this is 3D. So, the maximum value that we got was around 16 millivolts per centimeter Ørsted. You should compare that with a bilayer of nickel ferrite PZT, which is in hundreds of millivolts per centimeter Ørsted. So, in the nano system, the interactions are much weaker than in bulk composites or thick film composites. So, the second method we used is what's called magnetodielectric effect. Here we used special instrument capable of measuring the dielectric constant at very high frequencies, at microwave frequencies. So, you make the measurement with and without a static magnetic field. So, when you apply a static magnetic field, it will change the polarization, that will in turn affect the value of the dielectric constant, and that is what is measured in this procedure. So, it is called magnetodielectric effect, and you see here this is the dielectric constant measured as a function of frequency, and what is shown here is frequency range of 16 to 18 gigahertz, and that is the relative dielectric constant under 0 magnetic field and 2 and 4 kilo-Ørsted. You calculate the change in the dielectric constant and then plot the fractional change versus frequency, and this is the fractional change for a field of 4 kHz, and it's negative because the dielectric constant decreases when you apply a magnetic field. It's about 1 to 2%. And this one can also make the sample in such a way that it is in the form of a ring or a platelet. Then it has what is called dielectric resonance. This is dielectric resonance. Then under this resonance, the dielectric constant goes through a profile like this. Then you apply a magnetic field 2 or 4 kHz. Then find the decrease in the dielectric constant. Then plot the fractional decrease in the dielectric constant. It will show a peak through the resonance frequency, and this value here is close to 25% versus 1 or 2% here. So the overall magnetodielectric effect is amplified under this resonance. Right. So we also made a disk of these Cortical particles and then measured the polarization versus electric field with and without a static magnetic field. So the change in the remnant polarization, the fractional change, is plotted here as a function of h. So there is hysteresis in it. There is an increase in the fractional change with increasing static field. Then it goes up to a maximum of around 7%. For decreasing field, the value keeps increasing until it reaches about 14%. This is for barium titanate, nickel ferrite, DNA assembled disk. We also sintered these disks at higher temperature. The sintering, we thought it will give better compaction and a larger magnetic field induced polarization. We were somewhat correct. Here the maximum value is 20%, 14%. So after sintering the disk, there is an enhancement up to 20%. That's all. So, the question is, how does the Cortical particle behave compared to a bulk composite? So, instead of Cortical particles, what we did was we took nickel ferrite, maybe 20 nanometer, let's say, and then barium titanate 100 nanometer, mix them together, make a disk. They are not assembled into Cortical structure. They were just mixed together and then sintered at high temperature, and the measurements were done on those disks. That's the H-induced polarization. The maximum value here is anywhere from 4 to 8% compared to 14 to 20% with Cortical structure. So the Cortical structure does influence the nature of the magnetoelectric effect, and it enhances the effect in the way the structure comes up. If it is Cortical structure, it shows a much stronger magnetoelectric effect compared to just a bulk composite with random distribution of these two phases. Right. So this is the summary of what it discussed right now. We are able to assemble and demonstrate that our effort to synthesize particles with core of one phase, a shell of the other phase, we did succeed, and we followed two different procedures. One is chemical self-assembly, the other is DNA-assisted assembly, and then these particles were imaged by different techniques just to make sure that we do have the Cortical structure, and we are able to form superstructures in the form of thin films, 2D as well as 3D, and we made measurements of the strength of the magnetoelectric interactions, and from the values that we got, we infer that there is indeed a strong magnetoelectric effect, but not with a strength anywhere close to bulk thick films or thin films of these composites. So that is the take-home message from this effort. And I'll answer any questions you may have.
What is the difference between magnetodielectric effect and magnetoelectric effect?
Magnetoelectric effect is, you look for the change in a voltage produced in the structure because of mechanical strain, right? So, whereas in the magnetodielectric effect, you look for a change in the dielectric constant. That's the only difference. But both are measures of the strength of magnetoelectric interaction. So, you are measuring different parameters to come to the same conclusion, essentially.
Both will give same conclusion. Both effect, like magnetodielectric measurements and magnetoelectric measurements will give same conclusion about that.
Yeah, you can draw the same conclusion, of course. Because depending on what facilities are available in the lab, they can follow either one. So, people do all sorts of measurements. And we did have the facilities, so we just measured.
You made some theoretical estimates before designing the structures and all. You made theoretical estimates.
Yeah, but it's not a
And the formula
Proper.
can change at nano level, nano region and all. That because D33 coefficients and all that, those formulas were formulated for.
It will change because the geometry is different,
Yeah, that's
the mechanical connectivity is different. So depending on the structure, everything changes.
right.
There is no universal formula. So you have to
That's
come
what
up with,
then-
that's,
Then how can this for a formula be valid? Like how it was cross-checked and verified? Like these estimates you made.
we published all those formula. It's available in the literature. Yeah, so each configuration has its own equation for all these effects. So the magnetodielectric effect I talked about.
Mechanical coefficients were taken into these coupling coefficients were taken into consideration while
Yeah.
making this estimation and all.
Right. And also you use all the bulk values for Young's modulus, stiffness, all those things. But they are not exactly true. Because we don't have the numbers for nanomaterials. So that is a basic drawback in all these
It
calculations.
even requires tensor algebra and all.
Yeah, the formula is correct, but the numbers that you plug in, they are not correct.
That
So,
even I tried once for my particular samples, but I was lost.
yeah, if somebody can come up with the Young's modulus, all these parameters, magnetostriction and piezoelectric coefficient for nanoparticles of ferroelectrics and ferromagnets, the formula is already there. You can plug into those formula and come up with a number and then make comparison with whatever you measure. But otherwise, those numbers right now,
But I think to my best of my knowledge, nobody has reached the ideal values or something.
no.
Experiments have their own limitations.
Yes, yeah, there are limitations, of course, yeah. But we mentioned that in the papers. We do say that, these are using,
Recently published, the paper recently published.
it was, all the references are there. Yeah, right. So, it's 2016, 17. So, all this nano stuff is from 2014 to 2024. Any other questions? All right, thank you very much.